5.3b, we're going to use the general multiplication rule for independent events to compute probabilities. So the multiplication rule, if the two events are independent, is this. If A and B are independent events, then the probability that A and B both occur is the probability of A and B. Remember this notation, it's intersection, but it means and. Just do the probability of A times B. So in the previous lesson, I showed you a conditional formula to prove if things were independent or not. Now, if you're told they're independent, you can just jump right to this and make it very simple. The perfect games example. In baseball, a perfect game is when a pitcher doesn't allow any hitters to reach the base in all 9 innings. Historically, pitchers throw a perfect game in inning where no hitters reach base only 40% of the time. So, to throw a perfect game, a pitcher needs to have 9 perfect innings in a row. What is the probability that a pitcher throws 9 perfect innings in a row, assuming the pitcher's performance in an inning is independent of the performance in other innings? So that means from the first to the 9th inning, your performance on the first one will not impact any of the others and vice versa. So because they're independent, what you're trying to find is you basically want to find the probability of inning 1 and inning 2 and 3 and 4, 5 and 6 and 7 and 8 and 9. What you're going to notice, it's going to be the same number. So it's going to be something to the 9th power in this case. What's the probability of 1 perfect inning? That's 40%. So it's going to be 0.4 to the 9th power, and that's actually going to give you the answer of 0.00026. Overall, it's very close to 0. Now, just for a fact, in reality, it happens once every 4 to 5 years. So assumption of independence may not necessarily be a good one because it does happen. This would say the probability is close to 0, but it does. So independence maybe should not be assumed in this case because I could see in inning 1 you might get tired for inning 2 and so forth. So they might impact each other. Let's use this multiplication rule in the 4-step state, plan, do, and conclude method. Here we have a trimester screening where in the first trimester is a non-invasive test given during the first trimester of pregnancy to determine if there are any specific chromosomal abnormalities with the fetus. According to a study that was published back in 2005, approximately 5% of normal pregnancies receive a positive result. Among 100 women with normal pregnancies, what's the probability there will be at least 1 false negative if we're looking at 100 women? Well, let's just talk about how we're going to structure this. Let's state the scenario. The scenario is this. If 100 women with normal pregnancies are tested with the first trimester screening, what's the probability at least one of them will receive a positive test? So that's the scenario we're trying to simulate. What's our plan for this? Well, for our plan, it is reasonable to assume that the test results for different women are independent. So that does make sense. To find the probability of at least 1 false positive, we can use the complement rule and the probability that none of the women will receive a test. So if we find the probability of all 100 women and not one finds this test coming up positive, then if we subtract that from 1, which is the whole, that's going to tell us at least one of them will have the test come up positive. So let's do the do portion. So for the complement, what we're going to do is we're going to say the probability that a test is not positive is going to be the whole, 1, minus 0.05. So for a test to come back negative, which is what they want, is 95% chance for every woman. So based on that, what is now the probability that 100 women all test negative? Okay, well, they're all independent, so 0.95 to the 100th power is going to give me this value right here. So if this is the probability that they all are going to test negative, I want to know the probability at least 1 is positive, which means it's everything else. So what I can do there, at least 1 is positive, is 1 minus that value. So the probability at least one test is positive out of 100 women is 99.41%. Now, I will tell you, students tend to have a trouble with questions that say, what's the probability at least one of these happens? You want to star this example. This is exactly how you want to do them. It's the easiest way to do it. If you have to find the probability that at least one thing is true or one thing is false, what you want to do is find its complement and subtract it from the whole. Now let's make our conclusion. What we can say is there's over a 99% probability that at least one of the 100 women with normal pregnancies will receive a false positive on the first trimester screening. That's how you would state the answer in context. Now let's further explore independence versus mutually exclusive. We've talked about them separately. Let's bring them together though. Remember, the multiplication rule says the probability of A and B is the probability of A times the probability of B. That holds if the events are independent. Now, if they're not independent, you have to find a different probability way of getting the answer. Okay, the addition rule, which says the probability of A or B is equal to the probability of A plus the probability of B, that holds only if they are mutually exclusive. Remember, if events are not mutually exclusive, you have to subtract out where they overlap, or the probability of A and B does exist. Okay, now I'm going to show you this example here. If we have event A, that the person is male, event B, the person is pregnant. Are these mutually exclusive? Are they independent events? These events, mutually exclusive, means you have nothing in common. Clearly, yes, these have nothing in common, so yes, they're mutually exclusive. Now, are they independent? Will one not impact the other? So let me show you. The independence test, remember we did before, said find the probability in this case of B given A and see if it doesn't equal the probability of B. If they don't equal, we'd say no, they're not independent. There is some dependency. Well, let's talk about this. Let's find this probability right here. The probability of B given A. So what is the probability a person is pregnant given that they're a male? Well, that they're pregnant given that they're a male, 0. The probability, I don't care which room I'm in. If I'm in a room with 100 women and 100 men, this is going to be 0 no matter what. It can be nothing else. Fine. Now, let's assume we have a room of just both genders. So now the probability of B. What's the probability a person is pregnant? I don't know. It's just some number. There could be one woman in there that could be pregnant, and I'm not sure what the exact number is, but it's some number. Well, what that tells me is these are two different numbers, which means they are not going to equal, which means they have to be dependent on each other. So here's what this scenario basically tells us. If you have two events that are mutually exclusive in this case, they can never, ever be also independent. So mutually exclusive and independence can never happen at the same time. If one event happens, the other is always guaranteed not to happen. Now, I caution you on this because I have seen multiple choice questions in the past from the AP board where they ask you about these two events. And the multiple choice will say it's just mutually exclusive, it's just independent, it's both. It can never be both, and just really star this example for that. Let's look at another example, playing cards. We have a deck of 52 cards, 13 cards of the 4 different suits of diamonds, spades, hearts, and clubs. Determine if the events are independent, mutually exclusive, or neither. This is really good practice for this. So first example, event A, the card is red. Event B, the card is a club. So what they want us to find is the probability that we have a club, given it's a heart, and compare that to the probability of the club. Remember, whatever you put here is the probability you put there. Fine. What is the probability I get a club given I have a heart? Nothing. That can never happen. You can never give a club if you're just looking at hearts, so it's 0. Okay, what's the probability of a club? Well, the answer to that is 13 out of 52 is the probability of me actually getting a club. These two are not equal, so they are not independent of each other, so I know for sure it's not independent. Okay, are they mutually exclusive? If I'm a club, can I also be a heart? Those two can never happen at the same time. So because they can never happen at the same time, this clearly is a mutually exclusive event. Scenario 2. A card is red is event A, and the card is a 7 is event B. So to find this one, let's go ahead and find this scenario. The probability it's a 7 given that it's red, and compare that to the probability of a 7. Okay, the probability I get a 7 if I'm given a red card. There's 13 red cards. One of those would be a 7, so for my probability it would be 1 out of 13. Well, what's the probability I actually get a 7 out of the deck? Well, there's 4 cards that are 7s out of the 52, so that's what I have. Now be careful, they don't look alike, but they actually are the same. These two are independent, which means I know they cannot be mutually exclusive. It's impossible. So for this case, the answer is independent for the scenario. Scenario 3, event A, the card is red. Event B, the card is a heart. To set this one up, we're going to do this formula. The probability of a heart, given that it's red, compare it to the probability of a heart. So the probability I give a heart, given that the card is red. Well, there's 26 red cards in there. Half of them are the hearts, so that's going to be 13 out of 26. What's the probability I get a heart in the whole deck? That's 13 out of 52. This is what I compare. These clearly are not the same, which means they are not independent, so I can get rid of that. Are they mutually exclusive? If a card is red, can a card also be a heart? Absolutely, it could be the case, so they're not mutually exclusive. In this case, they're neither. Let's wrap this up with check your understanding. During World War II, the British found that the probability that a bomber is lost through enemy action on a mission over occupied Europe was 0.05, so 5%. Assuming the missions are independent, find the probability that a bomber returns safely from 20 missions. So ultimately, if you think about it, it'd be mission 1 and mission 2 and mission 3, and we'd go all the way to mission 20. What's the probability you return safely? So it's going to be something to the 20th power. So what is the probability you return safely? What you need in here is that probability. You've been given the probability that you get shot down. So what do you have to do in step 1 here is you're going to find the probability that one returns safely. Okay, the probability of that is 1 minus the probability was lost, or 0.95. Okay, once you have that, we're going to apply it to 20 missions, and they're independent. So what you can do in this case, we're all independent from each other, so now we can just jump right into the formula and do 0.95 to the 20th power. It's almost a 36% chance out of 20 missions, all the planes made it back safely. Here, government data show that 8% of adults are full-time college students, 30% of adults are age 55 or older. Since these two numbers times together get you 0.024, can we conclude that 2.4% of the adults are college students 55 or older? Why or why not? What they've done is they've chosen to multiply these two probabilities together. They chose to say that you're a full-time college student and you're 55 or older. If these two events are independent, you could say that. Now, in this case, no, we can't conclude that that's the case. Well, why not? Well, whether one is a college student and comparing that to someone's age, they're not independent from each other. So you can't say that. Far more younger people are college students than older people, that's true, but it could be some connection between that.